Hello and welcome back. In the last lecture we talked about random variables, and now we would like to start modifying them or talk about functions of random variables. Okay, so just like we noticed or observed for discrete random variables, it's very useful to talk about functions of random variables. For example, if someone's income is a random number x, then the amount of tax they pay is the random number y, which is, let's say, 0.3 times x. Okay, that's the income tax that they pay. Or if their driving speed is x and they get caught by a policeman, then maybe the fine that they're going to pay is a random variable y, which is 2 to the x. Okay, that's how much they'll need to pay. So what we have is that there's a random variable x distributed according to some distribution function fx, and we're going to assume that fx is some known distribution. So someone that's given it to us, and then we have a function. We have a random variable y, which is some function g of x, where g is a known and deterministic function. Okay, and what we're interested in is finding the distribution of y. Okay, f of y. So we're asking what is the distribution of y. Okay, and so I'm going to start with an example. So let me first describe this example. We'll make somewhat of a general example. So assume that a is some constant which is bigger than -1. Then the integral of a plus 1 times x to the a dx is x to the a plus 1. Right? Because if you take the derivative of x to the a plus 1, you get a plus 1 times x to the a. And therefore, the integral from 0 to 1 is x to the a plus 1 evaluated between 0 and 1. Okay, and that's just going to be 1 because it's 1 minus 0. Okay, okay, so that's one observation. The other observation is that what we have here, what we're integrating over is no negative. Okay, and what that means is that if we let fx be this value a plus 1 times x to the a between 0 and 1, okay, and 0 otherwise, okay, then fx is a PDF, right, because it's no negative and it integrates to 1. Right. So this is for a bigger than 1. We'll talk about a less than 1, a less than minus 1 later. Okay. So now we can look at the CDF of f of x, which is the integral from 0 to x of a plus 1 mu to the a d mu. And we already saw what is the integral of a plus 1. Well, here x to the a u to the a is u to the a plus 1. And so the integral is just u to the a plus 1 evaluated between 0 and x, which is x to the a plus 1, because we then subtract 0. Okay? So it's x to the a plus 1. And we're going to use a specific case of this where a is equal to 2. So in that case, we have what we have here is 3 times x squared. So and this f of x, this value holds between 0 and 1, namely below. So I'm sorry, this should be 0. Below 0, it's going to be 0, and above 1, it's going to be 1. Okay. So I was saying we're going to look at a, which is 2. So f of x is going to be 3x squared. Okay. And capital F of x is going to be just x cubed. Right. And x, again, is between 0 and 1. So above 1, it's 1. Below 0, it's 0. All right. So let's just repeat what we're using. This fx, which is 3x squared, and the CDF is x cubed for x between 0 and 1. So that's what's written here. 3x squared, x cubed between 0 and 1. Okay, and we're going to look at two functions, g. One is where g is increasing, and then after that we'll look here at g, which is decreasing. So for an increasing g, let's select g to be x to the 1.5. So y is g of x, which is x to the 1.5. So observe, it's a deterministic function of x. So once someone gives you x, then you know everything. All right. So we're interested in first, we'll calculate the CDF of y, okay, which is just the probability that y is less than or equal to some value y. Okay, and because x is distributed between 0 and 1, then y is also going to be distributed between 0 and 1 because y is x to the 1.5. So any number between 0 and 1, raise it to the 1.5, you get a number between 0 and 1. So we're only interested in y's that are between 0 and 1. Below that, f of y is 0, and above that, f of y is 0. Okay, so the probability that y is less than or equal to y and y is x to the 1.5 is the probability that x to the 1.5 is less than or equal to y. And we can just raise each side to 2/3. So it's the probability that x is less than or equal to y to the 2/3. Okay, and this, the probability that x is less than or equal to something, is just the cumulative distribution function of x at that point. So it's just fx of y to the 2/3. Okay, but fx of anything is that anything cube. So this is going to be y to the 2/3 cube. So it's y squared. So we see that we could find the CDF of y, and it's just y squared. Now we're interested in the distribution of y, the PDF, and so we need to differentiate the CDF. So therefore, but before we do that, just a couple of sanity checks. So remember that f of y is non-zero only between 0 and 1. Because y is distributed between 0 and 1, it's x to the 1.5. So if we look at the first point where f of y could be non-negative, that's 0. The cumulative distribution function at that point should be 0, and it is, right? Because we just plug in 0, it's 0 squared. And when we look at the last value that y could get, which is 1, then fy of 1 is going to be y1 squared, which is 1, which again is the way it should be, because this is the highest value that y can get. Okay, so both of those make sense. Okay. Now, as we said, we're interested in the PDF, not the CDF, so we just differentiate, and therefore the distribution of y is the derivative of y squared, which is 2y. Okay. Next, let's look at a decreasing function g. For example, x to the -3, or 1 over x cubed. Okay, so that's a decreasing function. And notice that this decreasing function, because x is between 0 and 1, and we look at 1 over x cubed, it's going to go it's going to be positive between 1 and infinity. Okay, so and which we'll say in a second. So fy of y, the cumulative distribution function, is the probability that y is less than or equal to y, which will be the distribution is positive only when y is bigger than 1, because we have 1 over x cubed and x is between 0 and 1. So this will be a number bigger than or equal to 1, between 1 and infinity. And the probability that y is less than or equal to y is the probability that, because y is x to the -3, it's the probability that x to the -3 is less than or equal to y, which is the probability that x is bigger than or equal to y to the -1/3. So just move to the other side and take the cube root. Okay, so it's probably that x is bigger than y to the 1/3. And the probability that x is bigger than y to the -3 is, we want to relate it to the CDF of x. So we write it as 1 minus the probability that x is less than or equal to y to the -1/3. And that's 1 minus the CDF of y to the to the -3. But the CDF of x at any point, as we said before, is just that point cube. So this is going to be 1 minus y to the -1. Okay. So we see that the CDF of y is 1 minus y minus 1 over y for all y bigger than or equal to 1. So let's see what it is at the very first point where y can happen, which is 1. We get 1 minus 1, which is 0. So f of 1 is 0, fy of 1 is 0. And if we look at the last point where it can happen, which is infinity, we get 1 minus 1 over infinity, which is 1. Okay, so again, that makes sense. So now we would like to find the PDF of y, and that's going to be the derivative of this. So it's going to be just derivative of 1 minus 1 over y. The 1, when you differentiate, gives you 0, and this gives you the minuses cancel, gives you y to the -2. Okay, so we could calculate here the PDF of g of x, and in both cases when g is increasing and decreasing, we needed to do here one more step. Okay? And what we want to do next is we want to not look at a specific function like x to the 3 over 2 or x to the minus 3, but we want to look at the general function, and we'll first look at increasing function. So, but we follow exactly the same steps. So fy of y is the probability that y is less than or equal to y. And y is some g of x, so it's the probability that g of x is less than or equal to y. And that's the probability that x is less than or equal to g inverse of y. And this is just fx of g inverse of y. And now we're going to let, instead of writing g inverse of y, we're going to write h of y. Just abbreviate g inverse of y. So this is fx of h of y. Okay, so fy of y is just fx of g inverse of y. Okay, so that's easy. Now we want to find the PDF, so we need to differentiate this. So fy of y is the derivative of this of fy of y of this function. So it's the derivative of fx of h of y, as we saw here. Okay, and when we take the derivative, we first need to take the outer derivative and then the inner derivative. So it's going to be f prime of h of y multiplied by the internal derivative, which is h prime of y. Okay, and the derivative of f of h of y is just the PDF of x at h of y, and then we still have this internal derivative. Okay, so so this is what we get here, and then let's see how it corresponds to what we have done before. So let's look at the example that we had. So we had fx was 3x squared. The CDF of x was x cubed, just the integral of that. And the function that we looked, the increasing function, was x to the 1.5, g of x. And the inverse was y to the 2/3, just the inverse of this function. And we found that the PDF of y was just 2y. So let's see what happens here when we did it in the general way. So here we have the probability that g of x is less than y. So that's the probability that x to the 1.5 is less than or equal to y. We wrote this as the probability that x is less than g inverse of y. That's the probability that x is less than y to the 2/3. Okay, and you notice this is exactly the steps we had before. And then this is going to be equal to fx of g inverse of y. So this is just fx of y to the 2/3. Okay, and this y to the 2/3, notice is here. Is h of y. Okay, so it's fx of h of y. All right. So now we come back here, and to get the derivative, we need to take the derivative of this function. So we get that it's the derivative of y to the 2/3 cube. So we can first take the outer derivative and multiply by the inner derivative. So it's 3 times y to the 2/3 square. And then the internal derivative here is 2/3 times y to the negative 1/3. Okay, and we can simplify it a little bit, and we get that 3 will cancel off 3 here. We get 2, and y to the 4/3 minus 1/3 is y. So we get 2y, which is the same as what we got before. Okay, so we can see we can just follow this recipe for any function f. Okay, any function g, I'm sorry. And the same would hold for g that is decreasing, and I'm going to skip it, but you can look at it here if you want. Okay, so when combined these two methods, you get that if g is increasing, then the PDF of y is fx at h of y, which is g inverse of y, times the derivative of h of y. And when it's decreasing, it's fy is again the same thing, fx at h of y times the derivative of h of y. H of y, remember, is g inverse of x, but now with a negative sign. So if you want to write it in a unified way, you can write that f of y is fx of h of y times the absolute value of the derivative of h of y, derivative of g inverse of y. And another way that's another formulation that is sometimes more useful actually to write it as is that fy of y, instead of the absolute value of h of y, remember this is the h of y is g inverse of y, and this is the derivative. You can write it as 1 over the derivative of g of x instead of derivative here of g inverse of y. So it's 1 over g prime of x. okay, times fx of x. And what is x? X is h of y. I'm sorry, x is x is h of y, or y, the point at y is g of x. So if we write it here, we kind of ignore the function. We circumvent the function h. So we're looking at the value y, where y is g of x, or x is h of y, as we had here. Okay, so we're going to use this formulation actually a few times. Right, so in short, we talked about functions of random variables, and next time we're going to talk about uniform distributions. See you then.